Hello everyone, welcome to my presentation. I'm Sihao Sun from Delft University of Technology, and the title of this presentation is called Upset Recovery Control for Quadrotors Subjected to a Complete Rotor Failure from Large Initial Disturbances. And this work is co-authored with Matthias Barth, Brun Streckfein-Scheindel, and Kuhn Divisor. As we know that the quad-rotor drones are popular in many industrial applications, and to improve the safety of this kind of drone, the fault-tolerant control technique is very important to prevent crashing after the failure of rotors. And the state-of-art research will sacrifice the yaw control of the quad-rotor, and instead they used the reduced attitude controller to control a body-fixed vector n to track its reference, and in such a way the position of the damaged quad-rotor can be controlled. However, the state-of-the-art work assumed that the drone is close to its hovering orientation, and using this assumption for their controller's design. But this assumption is invalid when the drone has a very large initial orientation, such as upside-down orientation. Therefore, the objective of this research is to design a fault-tolerant controller to recover the quad rotor with single rotor failure from a very large initial disturbance. Now let's have a look at the general control diagram. Our controller consists of three parts, and they are altitude and position controller, which transform the altitude and position reference to the reference of the thrust direction and the thrust magnitude. The second block, attitude controller, transforms the thrust orientation to the desired angular acceleration of the quad rotor. And third part, control allocation, use the above information to calculate the thrust command of each individual rotors. Now let's look at them in details. The first part, position controller, calculates the desired normalized thrust using a PID controller. And then we hatch this desired normalized thrust to prevent over-aggressive maneuver. And after which, we can obtain the desired thrust direction together with its magnitude. In the second part, namely the attitude controller, we can find a rotation direction NC that is perpendicular to both current thrust direction N and its reference. Naturally, the angular rate command is defined on this direction. So if the drone has these angular rates, it will finally align N with N desire. Therefore, we desire an angular acceleration alpha design from a PD controller. Now we have obtained the desired thrust and the angular acceleration. So the third block, control allocator, converts them to the thrust commands of each rotor. And this can be done by using a benchmark allocation approach by solving this quadratic programming problem. And here, mu is the desired total thrust and moment on the entire vehicle. And G is a mapping, and we call it control effective matrix, which maps the thrust of each individual rotor to the resultant thrust and moment. The second term in this cost function tries to minimize the control effort, and the constraints make sure that the thrust command given to each rotor satisfies the physical limitations. Unfortunately, we find that this benchmark approach does not consider the fact that one rotor is missing. And the direct consequence is that the damaged drone can rotate on some directions that is very hard to decelerate due to the rotor failure. For example, as this video shows, the drone has an initial angular velocity towards this damaged rotor. It will keep rotating and will never recover. Therefore, we need to find a way to solve this problem. We hereby introduce the attainable moment set, which is a set containing all the possible resultant moments generated from existing rotors. Where rotor number 4 fails, we can see that the original attainable moment set is shrinked to this yellow one. Consider the current angular velocity omega. It has a component omega tilde that is perpendicular to the boundary of the attainable moment set. And we can see that we cannot decrease it because there is no attainable moment that can be found from the other side of the center of gravity. Therefore, the strategy here is try to limit omega tilde. And what we do here is to predict the future omega tilde after a certain time horizon th by using the model of the quadrotor. And we set a boundary of this omega tilde. Then we can define a new quadratic programming problem, P2, as the control allocator. And this allocator contains the constraint on omega tilde, and we also add a slack variable d to make sure that the optimization has a solution. Now let's look at the performance of the P2 allocator in the simulation. The Quadrotors is also initialized with a large omega tilde, but you can see that the angular velocity on the undesirable axis is successfully suppressed. Instead, the drone chooses to flip on the direction where both rotors are functional. And finally, the drone returns to its original location. We can have a look at the video from the beginning again. Okay. We have validated our approach in the Monte Carlo simulation, and for each set of simulation, we run 200 trajectories initialized from randomly selected angular rates and orientations. And all these simulations started at an altitude of 50 meters. The first method is the benchmark approach, which is a nonlinear controller proposed in the reference 1. We have already tested in this approach even in high-speed flight. You may check the video from this link. We can see that over 50% of the simulations crashed, and most of them are initialized from an upside-down orientation, where NZ is positive. And the second approach is our method, but with P1 allocation. And you can see that most trajectories recover before crashing. Now, if we use the P2 allocation, we can clearly see that the recovery performance is dramatically improved. Actually, over 90% of them recovered before falling 10 meters. The model used for these simulations can be found in the second reference in this slide. We have also validated our approach in real life. In real experiments, we casually tossed the quadrotor into the air to create this arbitrary initial condition. When the drone is about 2 meters above the ground, the recovery control is triggered. The tested platform is a Parrot Bebop 2 quadrotor. The controller can run on this platform at 500 Hz. We use an extended Kalman filter to fuse the OptiTrack and the IMU to provide position, velocity, and altitude estimates. And this is the video of one of the recovery flights. And this is the video of the slow motion. We can clearly see how the remaining rotors take control and stabilize the quadrotor from randomly generated initial conditions. Now comes to the outlooks and recommendations for the future work. The first of all, we would like to conduct outdoor experiments without motion capturing system. Secondly, we want to take into account the center of gravity bias and the inertial parameter mismatch. And thirdly, since our approach is not an optimization-based approach, perhaps we can find a trajectory optimization-based methods to further improve the recovery performance, such as a modal predictive control. Last but not least, perhaps we can find a connection of this recovery strategy with the concept of flight envelope protection. Thank you for your attention. Please don't hesitate to contact us if you have any questions.